Hi guys, welcome to this YouTube video. I am Queenisha Nongkhlaw, MSc 3rd semester physics student of Assam Don Bosco University. So in this video, it's a short video by the way, which is a part of an assignment. I will talk about the interference of light. So without further ado, let's get right to it. Alright, let's take for example the sun, which is the source of light and energy. It emits the energy and the distribution of the energy is uniform across the medium, right? Let's consider two sources of light. Let's call them S1 and S2, which are monochromatic and have the same amplitude. Here, monochromatic basically means any light which is purely of a single color, okay? For example, like sodium light or yellow light. And each of these will produce waves. So, let's see what happens when the two waves interact. We have two waves here, A of S1 and B of S2. Now, let's see what happens when the crest of A hits the crest of B. In that case, we will get a bigger wave. Why? Because at every instant, the displacement of the two waves get added. So this is called the constructive interference. Now, what about if the crest of wave A falls on the trough of wave B? In that case, we will get no wave or zero wave because these will cancel each other out. So this is called the destructive interference. Now, this is the basis of interference of light waves. Let's check out what happens if you bring a screen in front of the two light sources. The waves from the sources of S1 and S2 need to travel some distance in order to reach this screen, right? Now, if the distance that wave A needs to cover in order to reach this screen is equal to the distance that wave B needs to cover to reach this screen, that is somewhere along the midpoint of the distance between the two sources, then they will be in phase. Like here, as explained earlier, the crest of A will fall on the crest of B, and in that case, the resultant wave is a bigger wave, that is constructive interference. So, in the screen, you will see a bright band or a bright fringe as we call it. Now let's go to another point in the screen below the bright band. So obviously, the wave of S1 has to travel more distance than that of S2 in order to reach the screen, right? What happens is, if the wave of S1 has to travel a distance of half a wavelength more than the wave from S2, then what will happen is, as explained earlier, the crest of A will hit the trough of B, and in that case, we will get no wave. This phenomena, which is also known as destructive interference. And on the screen, you will see no band, that is dark band or a dark fringe. Let's go further below the dark band to a point in the screen where S1 would have to travel one whole wavelength more than the wave from S2 in order to reach the screen. So what happens is they will be in phase, although S1 has to travel one wavelength more, but they will be in phase, and again constructive interference will take place and you will get a bright fringe. In this manner, you can go to different points on the screen at equal distances and you will find bright and dark fringes. The bright fringes occurs because, like I have explained earlier, the crest of one wave hits the crest of the other wave, and as a result, constructive interference takes place, and therefore you get a bright band. And the dark fringes occurs due to destructive interference because the crest of one wave falls on the trough of the other wave, and because they cancel each other out, and so we don't get any resultant wave, and hence you will get a dark band. If you look at the screen, you will see a series of dark and bright circular stripes which comes out from the center. That is, this bright band will be the brightest, and as you come out of the center, gradually the fringes will get dimmer and dimmer. Now, since the wavelength of light is very short, around say 400 to 700 nanometers, alright, so we can't see this effect normally. What we need to do is we have to view it using a microscope. Let's take a practical look at this phenomenon. Let's consider a monochromatic source of light and two narrow slits. Just make sure that these two slits are very close to each other and they lie at an equal distance from the light source. Now, if you can see on the screen, according to the diagram, the two slits, they will give out wavefronts in all directions. Now, because this is a monochromatic source of light, so these two waves will be of equal wavelengths and of the same amplitudes. If the paths are equal, then the light waves from the two slits will reach at one point, that is the central point, in phase. That is, either the peak or the trough of one wave falls on the peak or the trough of the other. And so at this point, the intensity of light, it becomes maximum. Now this is called the central maximum. If you move above or below the center, let's just go above the center, you will see at some points there, you can see the regions where it is dark. Now this is because the crest of one wave, it falls on the trough of the other wave, and so the resultant amplitude and hence the resultant intensity of light becomes minimum at these points. And because this is due to the destructive interference of light. So these points, they correspond to positions of dark fringes. This is the double slit experiment done by Thomas Young to demonstrate the interference of light experimentally. So that's all about the interference of light. So guys, if you do find this video to be informative, do like and share and put your feedbacks in the comments sections below. Thank you and stay safe.